for 12-minute talks and then a couple of minutes of questions, and then there'll be time for more discussion at the end, if you're good with that. And I'll give you a nudge at 10 minutes, so you have like 2 minutes to wrap up then. This meeting is being transcribed. Don't know what that means. Okay. Yeah, let's should we get started? We have about 50 people coming on. There's some more people filing through right now. And I think we are recording as well, right? Yeah, okay, good. So yeah, thank you everyone for coming. This is the 44th ECS and Cloud Feedback Virtual Symposium. We're excited to have you all here. But before we get started, I just want to give you guys a brief update on something I think important that happened over the past week, which was the weather and climate live stream. So for those of you who aren't aware of the situation in the US, federal funding for science is currently in a bit of an existential place right now. There have already been executive orders which have begun to damage the state of US federal funding for weather and climate science, and that there are proposed budget cuts which would make that an order of magnitude worse than it's already been. And to try and draw attention to this, myself and a number of others organized this 100-hour live stream where we got over 200 weather and climate scientists based in the US to come together and share their science to try and convince people why it's important. We had talks, keynotes, hurricane hunters who came and shared stories of surviving Category 5 hurricanes when they thought it was going to be a Category 3. We had Ask Me Anythings. We had people singing songs that they wrote about weather and climate, Q&As, and so much more. And I think it was a really unparalleled show of unity from our field, where there is, Carrie and others have written about this weather and climate schism, right? And I think this event was one of the first times I think we've really bridged that and had all of us coming together speaking with one voice about such an important issue. And I think in a number of different ways, it was a historical event. And so I want to thank everyone who took part. I know a number of people, we emailed, people in this community, and I think a lot of people stepped up to share their science and to speak out. And this wouldn't have been possible without you. So thank you so much for volunteering your time and your energy. We promised the speakers beforehand that we wouldn't keep the live streams up after the event. And so we've temporarily privated these streams. That means you can't find them on YouTube anymore. But we are going to be contacting today. We're going to be sending out an email to the speakers to see if people are to get opt-ins and opt-outs for whether people want us to, basically we want to re-upload the streams, but redacted. So we're going to email you today. If you want to opt out of having your portion of the stream public, that's completely okay, but just let us know. And we're aiming to get that done by end of next week, or start of next week. And just some data, which I thought was amazing. So one of the things that we were asking people is if they felt strongly about this issue and they wanted to support weather and climate science, we were asking them to reach out to their representatives with a link that we gave them. And we had, during the event, over 7,300 calls logged through this app. So it's probably underrepresenting the total amount of calls logged to people's local representatives, asking them to fund weather and climate science and to protect them from these cuts. And since the event ended, we've gone up to almost, I wrote this and then checked about 10 minutes later and it had gone up. Okay. But we had about 1,500 more calls done since the event ended. So like less than 24 hours ago, roughly that. Anyway, I'm really sleepy. And and we should keep calling. The event doesn't, our action doesn't end because the event ended. I'd encourage you, if you are a US citizen and are living in the US, to go to this link, wclivestream.com/act, put in your zip code and call your representatives. And you only get this view on the app if you've actually called them. So you know that I have. Now it's your turn to go and call them. And you can also give us feedback. For those of you who watched it, whether you're in the US or not, we have a little just exit survey that we're doing, wclivestream.com/next. We're just taking some basic information and feedback. So we'd really appreciate it if you took a minute to share your thoughts with us. And back to our regularly scheduled programming, we have three amazing speakers today. We have Helene from Max Planck, we have Nadir from down the office, NOAA GFDL, and we have Sarah from the University of East Anglia, who will be talking to us about clouds, climate sensitivity, and radiative feedbacks, and just basic symposium notes. All the talks can be about 12 minutes. We'll have a little bit of Q&A after each one, and then we'll have some time for discussion at the end. You can type comments in the chat at any time. We will ask you if you want to speak, if you want to actually unmute yourself and say them in the Q&A. And then you have this executive committee and a backlog of previous talks if you want to go see them. So yeah, with that, I'll hand over to Helene if you want to start sharing your screen.
Yeah, we will. Are you seeing it?
Yeah, we see it.
Which one are you seeing?
We see the right one.
Okay, you sure?
It's okay. And yeah, just take it away.
Okay, perfect. So I want to talk about the clear sky Longwave climate response as estimated from Reanalysis data. And when I started to look into the Longwave climate response, I first looked at the paper from Colin, or maybe not first, but very early on. And they showed that OER is linear with surface temperature. And this is nice because it, as you all know, it allows us to estimate the climate response in one climate and then assume it's basically the same in another climate. So if Earth warms, that's fine. And one key thing that they did was they assumed relative humidity to be constant in their single column model. And they tried several relative humidities and showed that this linearity holds for some of them. And this assumption is really important because it was used in many studies and models, in very simplified models, like those 1D column models, and they all come to a climate response estimate of roughly 2.2. And this is really nice. And I think it's super fascinating because this number changed so little in the past 60 years. So one could argue, if you've read Manab and Wetherald in 1967, you know everything. And this assumption is super important. And then we can ask, is it actually true? So on Earth, is relative humidity actually constant? And one very clever person once told me, it has to be, kind of, because what goes up also comes down eventually. And I think that's really convincing in a way, because that's how circulation works. But it does not have to come down at the same place. So if we look at the Reanalysis data sets and how relative humidity changes with warming, so we pick any point on Earth and then look at the development of surface temperature and how relative humidity changes in one specific temperature range in the atmosphere. So here we pick between 260 and 250 Kelvin, which is mid-atmospheric. It's really just an example. You could pick others, doesn't matter. But then you see that actually it changes a lot at each individual point on Earth. Globally, it's more or less constant. So if you average all those together, then you arrive at more or less zero. But locally, there's a huge change in relative humidity. And as you can see on the maps, the color range is a bit different between all them, but they also calculate relative humidity a bit differently. So don't focus on that. But the pattern is kind of similar between all of the reanalysis in this particular 15 years. So you get a drying over the warm pool and a moistening over the Atlantic in those 15 years. So even if globally relative humidity might be constant, locally it's not. And then we can ask the question, is that actually important? And the thing is, even if relative humidity was constant, and this is a really nice study that Brett and his colleagues did in 2021, it doesn't mean that the climate response is the same. And so this figure is also going back to a single column model where they calculated the climate response for different constant relative humidities and different surface temperatures. So x-axis is relative humidity, it's constant over the whole column, and y-axis is surface temperature. And I can't point, but what you see is that even for Earth-like conditions in this greenish box, we have local responses that are very different from this 2.2 plus minus 10%. And we can also see kind of that it is actually important how it changes locally, because if you look at higher temperatures, then there are more contour lines over the same range of relative humidities than if you look at lower temperatures. So putting this together, it would be nice to actually get a climate response for the clear sky from reanalysis. And then the question is, can we actually do that? And the answer is yes, we can, but it's not as easy as it seemed. So what we did was we took our reanalysis data, took the temperature profiles, humidity profiles, and surface values, because those are the most important things for the clear sky feedback, put them in a radiation scheme, and calculated radiation at each time point. And time point can mean different things. So you could do this on the seasonal scale, an interannual scale, or on a long term. But long term is a bit hard because you need like more than 100 years of data, which you don't have with reanalysis. At least you don't have 100 years of data that are actually reliable. And what we then did, and what you can see in the figure, is that we calculated this for each month in the seasonal case, which is the gray dots. Then you average everything together globally, and you get one radiation at the top of the atmosphere value for each mean global surface temperature. And then you can just put them on a plot, do a regression, and get a value for this. And if you want to get from the seasonal response to the interannual one, you have different ways to do that. You could either calculate radiation on a monthly basis and then average together, or you can average the profiles together annually and then calculate the radiation once. And this is the two different blues that you can see in the plot on the right. You can also do a similar thing and take all Januaries or all Julys and do the regression in those months and then average this together, which is the greenish is December, I think, and the orange is July. And if you do this, you get one estimate for the seasonal climate response, and you get 3 estimates for the interannual climate response. And the nice thing is that all of the interannual responses are more or less in each other's uncertainty, so you don't have to do it 3 times for each calculation you do. You can just pick one and say, okay, that's fine. What's also interesting here and visible, that all our estimates that we get, at least for those 30-year period, are smaller than we would expect. So I said before, for constant relative humidity, we want something like 2.2 from theory and single column calculations, but we actually end up with something like 1.8 or 1.9. So we are smaller. And the question is a bit why. And one problem is, and that's why I had this yes, but before, that for the first half of our period, so the first 15 years, this actually doesn't work. So we do get points, obviously, but they are far outside any range that we would expect. And also they differ a lot between the 3 reanalyses. So if you look at a yellow point, which is the result we get from MERA2, then it's far above what we would expect from the fixed relative humidity assumption, but also what we would expect from models like the AMIP calculations or coupled climate simulations. And JIRA and ERA, on the other hand, are lower than this estimate. And this gets a lot better if we look at the second half of this time period, which is reassuring because it tells us that maybe our observation system just got better and better over time. And then if we just look at a period where we actually had good relative humidity observation, then everything's nice and works out. But it is kind of bad because 15 years is very little to try to get a long-term or an estimate for an interannual feedback. So you could also look at the seasonal response. And the nice thing here is that it's it kind of is constant over time and also constant between the reanalysis. So we have some confidence that the seasonal estimate is actually kind of true. And there are other studies before that show that actually we wouldn't expect the feedbacks on different timescales to be substantially different. So, but those are also smaller than what we said before. So they are also at like 1.9-ish rather than 2.2. And the difference, so now we have to go back to the relative humidity because this is nice. And I said that I think it's because of the relative humidity. And you can actually kind of see that if you look at the tropical mean change in relative humidity with global surface warming, because then you can see in the solid line on the left that if you look just at the last 15 years, all of the reanalysis are kind of similar, except for Mera in the upper troposphere, which has a moistening there. But this is consistent with the climate response being smaller for Mera in the second period that we looked at. And the other two show a drying in the mid-troposphere and also the upper troposphere. And if you look at the dotted line for the first 15-year periods, they're super far apart, and this also explains why they are so different, why our climate response estimates are so different. But this also means that our estimate of like 2.1 that we got is associated with a drying in the tropics. And this is kind of bad, because if the atmosphere is drying, we would actually expect a larger climate response than from the constant relative humidity assumption. So if over a longer time frame, our atmosphere would actually contain the constant relative humidity, then the feedback might be even smaller than what we estimated. And those lines in the relative humidity are just an average of the maps that I showed before. And if you pay attention to those maps, they kind of look like a drying pattern that you would expect from El Niño years that we have. And that might be because we just have 15 years, or it might be so if the warming patterns actually becomes El Niño-like in the long term, then we would expect the numbers to be kind of right-ish, I guess. So all in all, we see that constant relative humidity doesn't hold locally, which is probably not really surprising, but I think it's important to note here because it actually has an impact on the global climate response. We see that our annual response that we get from reanalysis is pretty consistent after 2008, and it is caused, or it is caused by an El Niño-like drying, which leads to a response of 2.1, which means that if relative humidity was constant, we would expect an even smaller number than this. And you can read all of this in more detail in our paper that came out like 2 months ago. So thank you very much. If you have questions, please shoot.
Thanks very much, Helene. Great talk. We have a question straight away from Martin Kohler, which is, did we assimilate EASI from 2008?
Yeah, basically
yes.
changed in 2008. Yeah, that's my question.
Yes, it was. So I didn't say in the presentation, but we looked at this, and we can look into documentation, and we see there that EASI was launched in 2006, and then there's usually a period where the satellite is up but not used, and then they start using it in late 2007, basically. So that's why we use that as a cut. And beginning 2008, all of them have EASI for the remaining period.
We also have a question from Claire. I don't know if you want to unmute yourself.
Yeah, I just wanted to ask if those maps of relative humidity changes, how different they look at different levels. You said you were looking in the mid-troposphere, but is the spatial pattern really consistent?
Yeah, so I would say in the mid-troposphere, it is super consistent. So if you look at 10 degrees more, 10 degrees less, it really doesn't matter so much. It is a bit different if you look very high up, so between like 220 or 240 Kelvin. So there it looks different, and also very close to the surface. But in this mid-tropospheric range, it's pretty consistent, I would say. So we checked between 270 and 240, I would say it's pretty much the same, obviously with some variation.
Cool. And just in the last minute, I'll read, Karsten, I'll read your question for you for speed, just for time's sake. What about the influence of transient warming, particularly over land, where you can have stronger warming, which leads to drier conditions temporarily? I think you mentioned ENSO, but is there a role for land warming?
Yeah, we did separate in land and ocean when we calculated the radiation, but I haven't really looked at the influence of land. So the contribution to the feedback in total is not so big because just the area of ocean is so much larger than land. So I would have to check again. I'm sorry, I don't know. But I'm convinced that our results are influenced by transient warming because we only have 15 years.
Yeah. Great. Very cool work. Thanks, Helene. If you want to stop sharing, Nadir, you can bring up your slides.
All right. Let's see here. You seeing that?
Mm-hmm. Yep, take it away.
Okay, great. Well, always good to be here at the ECS Symposium. And so this is an introduction to a review paper that just came out on Friday, authored here with a number of GFDL co-authors, whom I want to acknowledge. It was just a pleasure working with them. Between them, they have decades of modeling experience, which I was able to benefit from. And as folks on this call know, GFDL has a long history of studying climate sensitivity, and in some respects, this paper was an effort to kind of maintain that tradition and hopefully push it forward. So again, as folks know, so equilibrium climate sensitivity has become synonymous with climate sensitivity. You know, there was this paper about 10 years ago urging the community to focus on this and to narrow the bounds on ECS. And it seems to have worked. And 4 or 5 years later, we have this omnibus review, the Sherwood paper, which many folks across the community and on this call contributed to. And it seemed this effort succeeded. And in particular, the likely range on ECS was reduced by a factor of 2 with this report. Also in the last handful of years, this very venue has arisen, which has been wonderful, and ECS is in the title. And in papers that look at climate sensitivity, the focus is typically on ECS, and often other measures like TCR aren't studied or emphasized. And so part of the point of this review was, especially since the advent of the Sherwood report and all the progress we have made on ECS, is to maybe zoom back out a little bit and consider the broader landscape. And so here's kind of a list of these different metrics of climate sensitivity. And it's kind of a long one. We've got the CES sensitivity, ECS, the TCR. These are all likely very familiar to this audience. There's a couple more metrics that actually arise in the context of Earth system models, and they quantify the emissions of the climate, the sensitivity of Earth's climate to emissions rather than CO2 concentrations. And these are the TCRE and the ZEC. These measures are more comprehensive. I won't talk about them a lot in this talk, but they're discussed in the paper. And these are actually the measures that are the most policy relevant and that form the basis for net zero policies, for carbon budgeting, and hence for international negotiations. And I think it's important to consider them along with the more physical climate metrics. Another interesting thing is that this set of metrics can be arranged hierarchically, and that hierarchy mirrors our climate modeling hierarchy, where the CES sensitivity is naturally calculated in an AGCM, TCR is naturally calculated in a coupled model, TCRE and ZEC are calculated in Earth system models. And when you arrange things this way, the natural place for ECS is actually in a slab ocean model, which is where ECS was calculated for decades up until really the 5th IPCC report. And what's happening as you move across this hierarchy is that important boundary conditions like the CO2 concentration, the ocean heat flux convergence, or the SST go from being prescribed to being interactive in a gradual way. And as you do this, you're of course including more processes, more complexity. And if you try to write down analytical expressions for these different metrics, these additional processes are encapsulated in additional parameters such as the heat uptake efficiency, gamma, or the airborne fraction of emitted carbon, alpha. And furthermore, this complexity is nested in the sense that these more complex metrics, like the TCRE on the ZEC, depend on the metrics that came before. So in the paper, we do survey all these metrics and derive these expressions and discuss them. For the purposes of this talk, I'll focus on the TCR and its potential utility. And just a plug here, if folks are interested in ZEC, there's actually a nice talk on this by collaborator Nathaniel Tarshish in the ECS Symposium late last year. All right, so to derive this formula for the TCR and to give us a way for thinking about it, we'll appeal to the two-box model, which again, folks on this call are likely familiar with. We have a mixed layer and deep ocean with corresponding temperature anomalies, a radiative forcing F, radiative response to space, lambda Ts, and then a deep ocean heat uptake, which is given by the heat efficiency, the efficiency of ocean heat uptake, gamma, times the difference in temperature anomalies. And you can write down the corresponding equations. We've got temperature tendencies and heat capacities on the left, and then these terms are just the arrows. And the reason I write down the equations is a couple-fold. One is that by plugging in numbers for these heat capacities and parameters, you can actually derive timescales for the equilibration of both the mixed layer ocean and the deep ocean. And what you find is that a typical equilibration timescale for the mixed layer is a few years, but for the deep ocean is multi-centennial. But of course, climate change that we are experiencing and care about is kind of more on a multi-decadal to maybe centennial timescale, so on a timescale in between the timescales of the mixed layer and deep ocean, if you believe the two-box model. And that's something we can talk about. And so in that case, if you're really working on these multi-decadal timescales, you can make the approximation of mixed layer quasi-equilibrium. And by that, I mean that if you're in between these two timescales, then you can assume the deep ocean hasn't really warmed significantly yet, because you're not close to this sort of multi-centennial timescale. But if the timescales you're interested in are longer than tau s, then you can assume that the mixed layer has kind of equilibrated to whatever the forcing is. And so you can assume that this time tendency is in this equation is small relative to the other terms, and so you neglect it. And so that means we can cross out a bunch of these terms. And so there's no time tendencies anymore. And so what's left is just an algebraic equation for the surface temperature, which we can solve and get this very simple expression. And this simple expression has a simple interpretation. It just means that the forcing, exactly in this expression by the increased radiation to space and the heat export to the deep ocean. And so that's an idea that may be familiar, but something striking about this is that it implies a linear relationship, a proportionality between temperature to forcing that's been utilized here and there in the literature, but I'm not sure that its generality, especially across scenarios, has been emphasized. And so that's something that I want to talk about. So Gregory and Forster looked at this in one climate model a number of years ago. So I wanted to revisit this in GFDL CM4. And so we're going to take a few different scenarios, the historical scenario extended to SSP 2-45 and also 1%. And we're just going to look at forcing versus temperature and see to what degree are they linear. Of course, for this, I'm going to need forcing. And so we're going to calculate that as effective radiative forcing from additional fixed SST runs that we did. And here's what you get for the historical case with all forcing agents. And it looks roughly linear. There's these additional dots down here that seem to deviate from linearity. And we can discuss this in the Q&A, where those come from. But then we can run other scenarios. We can redo the historical case, but with greenhouse gases only. And you get a very similar linear curve that lies on top of the all forcing case. we can run with aerosol forcing only. So now we get only negative forcings and negative temperature responses. But again, the slope is pretty similar. And we can just take the standard 1% CO2 run to 140 years, so up to quadrupling. And again, it lies along the same line. And so you seem to get this collapse of different scenarios onto the same curve when you just plot forcing versus temperature. And this is also what Gregory and Forster found. Pushing on this a little bit further, from this mixed layer quasi-equilibrium approximation, we had this expression for temperature and forcing. If I evaluate this at year 70 of a 1% run, then the temperature becomes the TCR by definition. The forcing becomes just the forcing and doubling. And if I combine these equations, then I find that I can get the temperature at any time just by scaling the TCR by the forcing. And this equation is general across transient scenarios. We're not specifying any scenario here. And indeed, if I just plot the scaling using CM force TCR, it seems to capture the behavior across scenarios. So that's nice, but this is just one model. How general is this result? Does it hold across other models? Now, for this, we'll need the effective radiative forcing, which in the past has really been a hang-up because models typically haven't reported forcing in the past. But with CMIP6, we did have this RFMIP, radiative forcing intercomparison, which is a game changer because now there's several models that or many models that reported their forcing, and some of which even did these sort of more laborious time-dependent forcing calculations. So there were 6 models that had the output that we needed. And so we have the forcing for each model from these fixed SST runs. We have the surface temperature on the x-axis from the usual coupled runs. And we have one scenario, the historical extended to SSP 2-4.5. And this is what you see across the models. You see variations in, in how much they warm, but there's a fair degree of linearity across them.
2 minutes.
Thank you. And if we have this the scaling, then we can take each model's TCR and apply it, and we get this. And so I would say that to first order, it does look like this linearity holds across models. Of course, you do see some deviations at late times or large temperature, and that's due to a combination of the slow component of warming and the pattern effect. And some follow-up work that we're doing actually suggests that the pattern effect is the dominant effect. All right, so we have this nice scaling. Can we do anything with it? And I would argue, yes, we can. So let's assume that the TCR of your model is known and you have some projection for the forcing time series. Then I'll argue that you could use this to estimate the time at which you might meet some temperature target. Because I can just take this equation and put the time dependence on the left-hand side, and everything on the right-hand side is a constant. And so if you have the forcing time series, then you just ask it, when is the forcing big enough so that it gives you this temperature response so that it equals the right-hand side. And so, and if you can do this, then the only information you need from the GCM is the TCR and a forcing time series. You don't need coupled runs for every different scenario, potentially. Okay, so let's test this idea in the same scenario that we've been looking at, this historical SSP 2-4.5. So on the horizontal axis, I'm going to take the actual temperature simulated by the model. I'm going to smooth it, and then I'm just going to ask, when does that smooth monotonic temperature time series cross a given target, like the 1.5 degree target? And on the y-axis, I'm going to estimate that time by solving this equation where T star is whatever my temperature target is. So I'm going to do this for the 6 models. So this is the result for the 1.5 degree target. And you see there's a good amount of spread. Some models think we've already hit the target. Some models think we won't hit it for decades. But the simple estimate captures this spread with a high degree of accuracy with an R squared of 0.9, so capturing about 90% of the variance. If I use a temperature target of 2 degrees Celsius, I get something similar, even more spread now because the perturbation is larger. But again, the simple formula seems to capture the spread to a large degree, again, an R squared of close to 0.9. And one thing I want to emphasize here is that this dashed line is not a best fit line. This is not an emergent constraint. This is an a priori constraint, and the one-to-one line comes from theory and existed before I put the data on there. So that's just an important thing to note. So hopefully this underscores the utility of TCR for near-term climate change, and maybe might redirect our focus to some of these other metrics that also bring in important additional physics like ocean heat uptake. So with that, these are just the take-home points. There's a hierarchy of interconnected climate sensitivity metrics. Studying TCR in particular gives you this linearity, which holds across scenarios in one model and seems to hold across models. And if you take this seriously, you get this scaling, which seems sufficient to predict with a reasonable degree of accuracy multi-decadal climate change. So with that, I'll thank you for your attention and happy to take more questions.
All right, great talk, Nadir. Do you have any questions? People want to raise their hands. Christy, go ahead.
Hi, Nadir. Nice talk, nice paper. I have a quick comment and then an actual question. The first one is that you've somehow missed the most common definition of ECS, which is in an atmosphere ocean GCMs where SSTs do evolve. But the question is, you're arguing that TCR is the better predictor on societally relevant timescales, but have you given any thought to this result of I think it was Gross et al. 2020 that shows that actually if you look regionally, ECS and T140 is a better predictor of regional warming than TCR?
Yeah, so let me get back to a couple of comments. Yes. So let's see. So one comment I'd make is just that you do get a very good correlation with ECS if you just correlate this the time to crossing a temperature threshold against ECS. You get correlations that are just about as good. And so I think that's consonant with what Gross et al. Found, and there's been a number of follow-up papers as well. I mean, one thing I'd argue here is, again, that this is an a priori constraint, not an emergent constraint that depends on the data. The other thing about that Gross et al. Paper is that the follow-up papers, at least in terms of my reading of them, sort of show that the answers do depend on, whether ECS is, whether ECS or T140, give the best estimates of climate change depends on timescale, scenario, how far out you go. Certainly going further out, TCR does less well than other metrics. So I think there's a little bit of a dependence on exactly what question you're asking there.
Okay, thanks.
Cool. I don't see any other hands up at the moment, but if you have questions for Nadir, put them in the chat and we might get back to them in the end discussion as well. So Nadir, if you want to unshare, and Sarah, you can share your slides.
Sure. Bear with. Okay, is that up?
Yes. Yeah, it's up.
Okay.
It's good.
Great.
Take it away.
Cool, thank you. So hi, my name's Sarah. I'm based at the Climatic Research Unit at the University of East Anglia. Today I'm going to be talking to you about some work that was recently published in Geophysical Research Letters. And if you were at the Climate Sensitivity Pattern Effect Radiative Feedback session at EGU, you will recognise this talk, where I'm going to be introducing you to our work and talking about climate models underestimating global decreases in high cloud amount with warming. So in this talk, I'm going to whiz through cloud controlling factor analysis. I'm going to imagine several of you are familiar with cloud controlling factor analysis, but you might notice some key differences in our framework to yours. But if you're not familiar, this will be a nice introduction. And then I'm going to whiz you through cloud feedback constraints using cloud controlling factor analysis and talk about our implications and conclusions. So throughout this talk, I'm going to be specifically looking at feedback from changes in high cloud amount. So I'm going to be looking at both the long wave and the short wave components of this feedback. But for now, it's just high clouds and changes in high cloud amount. So to whiz you through some background, as many of us are aware in this group, cloud feedback is one of the leading sources of uncertainty in climate model projections of the ECS. But cloud feedback constitutes several different processes, and these both contribute different magnitudes and uncertainties towards the net cloud feedback. So this figure on the right-hand side from Shoad et al. 2020 categorizes the cloud feedback into sort of 7 key different mechanisms. Several of these mechanisms affect low clouds, but there are 2 sort of key processes affecting high clouds, such as the high cloud altitude feedback and the tropical anvil cloud area feedback. In recent years, there have been some really awesome cloud controlling factor analysis derived constraints on both the total cloud feedback, so the net cloud feedback parameter, and also low cloud feedbacks. But high cloud feedbacks are not typically a focus of these cloud controlling factor analyses or observational constraints. And that is despite, for example, the anvil cloud feedbacks contributing a significant source of the uncertainty in the net cloud feedback parameter. So this is sort of the motivation behind this work. So essentially, can we use cloud controlling factor analysis to constrain high cloud feedback, specifically high cloud area feedbacks? So for those of you who aren't familiar, cloud controlling factor analysis we can use to derive sensitivities for a cloud radiative anomaly to meteorological drivers or the cloud controlling factors. So for a given cloud radiative anomaly, DR, on this left-hand side here, we can say this is approximately equal to the partial derivative of this cloud radiative anomaly with the cloud controlling factor. So dr over dCCF is the sensitivity, or theta, to the ICCF, multiplied by a change in that cloud controlling factor. So to visualize this, for every 5 degree by 5 degree target cloud radiative anomaly, we can say a change in this anomaly is equal to the sum over all sensitivities to all cloud controlling factors. I've cryptically put a question mark where I have the number of cloud controlling factors because we have a lot of partial derivatives. We actually have 1,386 partial derivatives per cloud radiative anomaly. This is because we don't look at local cloud controlling factors only. We look at cloud controlling factors with an 11 latitudinal grid box multiplied by 21 longitudinal grid box direction surrounding that central grid cell for 6 cloud controlling factors. So this setup has been chosen based on sort of rigorous statistical analysis. If you're curious to find out why we chose 11 by 21 and why we chose these 6 cloud controlling factors, the articles listed are at the bottom of this page. But we use surface temperature and upper tropospheric static stability, which are kind of the 2 cloud controlling factors I'm going to focus on in this talk, amongst others, including vertical velocity, relative humidities, and upper tropospheric wind shears. So I'm not going to get into why we choose those now, but just know there is a reason for these, and these have been chosen specifically for their relationship with high clouds. So once we've learnt these thetas, these sensitivities, we can use these to constrain the cloud feedback from climate model projections. So if cloud feedback lambda is equal to the change in the radiative anomaly with global mean surface temperature change, dt, we can substitute dr for our dr on the previous slide, which is theta multiplied by dCCF. To observationally constrain the cloud feedback, we can use observed thetas, so learning theta from observational records, and we can multiply that by climate model projections of the cloud controlling factor response to global mean surface temperature increase. So to visualize this, we have this panel at the bottom. Panel A shows an observationally derived sensitivity for the long wave component of the high cloud amount radiative anomaly. So this is the sensitivities, thetas. Panel B is the cloud controlling factor response derived from 4 times CO2 projections and climate models for surface temperature. And panel C is essentially panel A multiplied by panel B, which gives us the surface temperature component of the high cloud amount feedback for the long wave. So imagine we have that for all of those cloud controlling factors. We sum those together, and that is our observational constraint for the long wave high cloud amount feedback. So with this approach, we can quantify several different sources of uncertainty. So we look at observational uncertainty, we look at climate model uncertainty, and actually the uncertainty from our model and our approach itself. So are these cloud controlling factors doing a good job of capturing the cloud feedback from within climate model projections? So these 3 key sources of uncertainty are included in our observational constraint. So without further ado, let's get into our results. So as I mentioned, we're looking specifically at high cloud amount feedbacks. I'm going to walk you through the long wave results, but the short wave results are very similar due to the opposing nature of changes in high cloud amount. So for example, a shrinking and high cloud amount would result in a negative long-wave cloud feedback due to reduced absorption of terrestrial long-wave radiation, but a positive short-wave cloud feedback due to reduced reflection of incoming solar radiation. So if we look at this top few panels, on the left-hand side, we have the long-wave observational constraint for the global high cloud amount long-wave feedback. You can see in the climate models, the little scatter points, the climate model high cloud amount feedback is partitioned approximately evenly into negative and positive cloud feedbacks from the 16 climate models that we have available to calculate this from. But our observational constraint is robustly negative. So the 90% confidence interval is below the zero line. If you look at the spatial distributions of the observationally constrained cloud feedback and the actual cloud feedback diagnosed from the available climate models, you'll see that spatially these look really, really similar. So we have that negative long wave cloud feedback over the maritime continent, Indian Ocean, Western Pacific, and then the positive cloud feedback in the east. This is true for both the observational constraint and climate models. Similarly, for the shortwave results, we get a similar picture, except we have robustly positive shortwave cloud feedback now from our observational constraint. So what's actually causing this? We can repeat this analysis, but using the actual cloud fraction instead of a radiative anomaly in our model. So using that same equation from earlier on, we just plug in cloud fraction instead. And we find that the observations are indicating stronger decreases at a global scale. So the bottom left panel is a sort of global constraint. So observations are indicating a stronger decrease in high cloud amount with warming than the climate models suggest. Although the long wave and short wave components of the high cloud amount feedback are robustly negative and positive respectively, the actual net cloud feedback as a result of these changes is neutral. And this is actually the same as these climate models, which you can see in our paper that I've linked at the end of this article. And this is actually a result of the climate models getting the right answer for the wrong reasons. And we'll see that in just a second when we look at the sensitivities. So why are climate models predicting smaller or slightly less global decreases in high cloud amount with warming? Well, we turn to the sensitivities, those thetas, to investigate what's going on. So I mentioned that we can visualize the sensitivities that we learn from observations and also climate models, and we can plot these. So this figure, the left-hand side are the surface temperature sensitivities, and the right-hand side are the static stability sensitivities. Top panel is observations, bottom panel is models, just for the long wave component here, but a similar picture emerges for the short wave, just with the signs swapped over. So in the observations, you'll notice that we have these regions of negative sensitivity that aren't present in the models. I'm going to mainly focus on stability just for the purpose of this talk, but we do also investigate surface temperature in a similar fashion in the paper. So a negative static stability sensitivity over the maritime continent, Western Pacific, and mainly the deep convective regions, we find as observational evidence for the stability iris mechanism. So as static stability in the atmosphere increases, the horizontal outflow is suppressed, thus shrinking the high clouds. This, in the multi-model mean, at least, the bottom panel, is not present. And you'll notice that there's hatching, and this is where 80% of the realizations share the same sign. So this is actually because the climate models, some of them have negative sensitivities, others have positive.
2 minutes.
So there's not great agreement between the climate models. So first of all, we wonder, is this because the climate models have different sea surface temperature patterns? And so that's why in the multimodal mean, they aren't getting a relatively neutral sensitivities in these regions. So we repeat this experiment using AMIP simulations instead of CMIP simulations, so prescribing a sea surface temperature pattern of warming. But we find the same issue is present with the AMIP sensitivities as well as the CMIP sensitivities. So you can see, for example, the mean AMIP and CMIP SUT sensitivities, so this is the x-axis, are neutral with widespread. Therefore, we think the relationships are not being captured well by most climate models. So is this due to sea surface temperature patterns, this kind of neutral mean climate model sensitivity? Not entirely. We find this as evidence for a misrepresented stability iris mechanism. As I already mentioned, increasing stability reduces the convective outflow due to decreasing divergence. So this is present in some models, but doesn't seem to be present in all of them. In fact, it seems to be getting the completely wrong sign in some of them. So to conclude, our framework can predict the 4 times CO2 high cloud amount feedback very well. And we find that observations suggest stronger negative and stronger positive feedbacks for the long wave and short wave components of the high cloud amount feedback due to stronger decreases in high cloud amount. We also find that the observationally constrained net high cloud amount feedback is approximately neutral, and this is due to climate models, which is the same as the climate models, but this is because some of them get the right answer for the wrong reasons. And finally, we find evidence for a misrepresented stability iris mechanism in climate models. So thank you. I've linked the article here if you want to go read it. Any questions that you aren't able to ask me today, please do send me an email. And yeah, I look forward to answering your questions now.
Fantastic. That was a great talk, Sarah. Thank you very much. We had some questions straight away in the chat. So Thorsten, Isaac, and Claire. Thorsten, do you want to unmute yourself?
Hi, Sarah. So I was just wondering, and you probably explained it, but how you could separate height from area in the observations?
So we use the cloud histogram data from MODIS or from climate models that have run the ISCCP simulator. So they provide binned cloud amount by cloud top pressure and cloud optical depth. So we essentially just choose clouds that are higher than, I think it's 680 hectopascals. So anything above, with a height above this, we consider a high cloud for the purpose of this analysis.
Okay. Yeah. Yeah, but there might just be a little bit of risk mixing them up in the.
So mixing the mid and high level, you mean?
Yeah, or height or mount. It's kind of hard because MODIS just depends on the fluxes, right? It's a passive measurement. But anyway, really nice, interesting.
Thanks. Isaac, do you want to unmute yourself and ask your question?
Yeah, it was a nice talk. Thank you very much. And it's probably in the paper, but how sensitive is your result to the choice you've made about the horizontal extent of the predictor region?
Yeah, so the actual central estimate of the for the cloud amount feedbacks is not particularly sensitive. You get different uncertainty ranges. So we ended up going for a larger spatial domain, so 21 by 11 or 11% by 21, as this seemed to do a better job of picking up or the out of sample prediction. So using the larger spatial domain did a better job when we were trying to predict the cloud feedback from the climate models using climate model derived sensitivities. This isn't the case if you look at low clouds, for example. You find a slightly smaller domain size does a better job. But we think this is to do with the thermodynamic predictors, so surface temperature and static stability, under forcing become the patterns become more important. So we do discuss this briefly in the article, but this was kind of something investigated as part of the setup for this. So looking at different domain sizes and how well they worked out of sample. So yeah, to answer your question, the central estimate isn't particularly sensitive, but the uncertainty ranges can vary a little bit.
Okay, thanks a lot.
Great. And Claire, do you want to ask your question?
Yeah, thank you. I also had a question about kind of how you chose your cloud controlling factors, and in particular, if you could explain like why you were looking at RH at 700 hectopascal rather than somewhere, closer to the high cloud region.
Yes, so we do use both. So we use, hopefully you can see. Sorry, I'm on a not optimal laptop for this setup. So we use RH 700 we tried a whole range of different things. We ended up settling for relative humidity at 700 hectopascals as well as the upper tropospheric relative humidity. So first of all, yeah, we do use a measure of relative humidity that's closer to the high clouds, but also relative humidity at 700 hectopascals as a measure of sort of lower level moisture that might be available for convection. So we use both measures as we found it works well. And both of them are important predictors, particularly under historical conditions. So kind of if you look at historical validation, so month to month variability, both of them are quite important. But as you move towards the 4 times CO2 situation or setup, they become relatively less important than, for example, surface temperature, which is one of the most important ones under 4 times CO2. So yeah, I hope that answers your question.
Yeah, thanks.
Fantastic. We have a couple minutes now at the end. If anyone had questions for any of our speakers at this point, so Helene, Nadir, or Sarah, I can't, or you can raise your hand. You can just unmute yourself. You can put something in the chat. There was a little bit of a discussion about this curvature in Nadir's plot. I don't know if you want to just briefly feedback on that, Nadir.
Sure. Yeah, that curvature is there. It may be not surprising to folks because we know that it was derived under an assumption that the deep ocean had not warmed significantly and hadn't fed back on the surface. It also neglects any time dependence in lambda. And we know from a lot of the work done by folks in this community that those assumptions don't hold strictly, and certainly not over longer timescales. So you would expect some deviation at longer timescales. It looks like that linear approximation is reasonable if you're trying to predict when we cross 1.5 or 2 degrees thresholds. So sometime this century, as you go beyond the century or beyond or in say a 4x run past year 100, the deviations start to become significant. So yeah, it's just a reminder that it's an approximation on kind of multi-decadal timescales.
Mm-hmm. And maybe just, or Martin, were you going to speak? Sorry.
I just want to say thank you. Yeah, for longer scales, I understand. Yeah, no, thanks, Nadir.
There was also a question a little bit about Gregory, like what's the role, like where does Gregory regression fit into your table? Like where does it fit into this hierarchy?
Yeah, there's some discussion of that in the paper. So of course, I mean, you can calculate ECS any number of ways. Well, there's several ways, right? So I mean, ideally, we would just take coupled models and run them to equilibrium. And in the paper, we have 1 or 2 models at GFDL where we've done that. And then you're getting all the feedbacks you want. You're getting change in ocean circulation, ocean heat flux convergence, but it's just not practical. And so then there's a question of, the Gregory method. Is it, how satisfactory of a workaround is it? And I think there's probably a diversity of opinions on that. And I think it's, suitable for some purposes and maybe not for others. The thing that surprised me and sort of thinking about all these metrics, putting them all together, was that arranging them hierarchically, it sort of seemed like the slab ocean model should be part of the hierarchy, and then ECS was the thing that they were sort of, ideal for calculating. ECS is ideally calculated in a slab ocean model. You do it in 30 years. There's no issues with precision, because you can get a nice, you can average and get a precise value. It may not be accurate because you have this assumption of ocean heat flux convergence, and I think that's a legitimate concern, and especially in regions of sea ice where that fixed OHFC assumption is not natural. So anyway, this may just reflect my own sort of surprise that, oh yeah, I guess there's maybe a reason that we were doing that historically. There's reasons also I think we've deviated from that, but it was interesting to contemplate the trajectory.
Mm-hmm. I'd also just add that Karen Shell has this nice paper in 2013 because in CMIP3 we used to have slab ocean models in addition, so you can just see what the feedbacks are like, and they correlate very well between AOGCM and slab, which is kind of cool. Yeah, we have time for Mark, you were first, then Thorsten.
Yeah, I'll be quick. This is also for Nadir. Nice presentation, Nadir. That was really cool. One thing that struck me in yours is this really tight linearity between temperature and forcing, even across experiments. So like the aerosol only. And I'm trying to reconcile that with this whole concept of forcing efficacy, which would I believe give you a different slope. And is the magic there that we're using the effective radiative forcing, which tends to remove these kind of efficacy things? And should we kind of abandon the whole efficacy thing because it's really not real? It's something that kind of was an artifact from not using adjusted forcings and not really accounting for things like pattern effects. What's your thoughts on that?
What a great set of questions, Mark. It's something I thought about in writing the review. It does seem like when you do effective radiative forcing, a number of the efficacies start to kind of collapse closer to 1. There was a nice paper, I think, by Richardson within the last handful of years that showed that, although for aerosol forcing, there are some models, not all models, for which even with ERF, the aerosol ERF is the aerosol efficacy is different from 1. So I feel like the jury's still out. It feels like most of the non-unit efficacies kind of disappear when you do ERF, but not entirely. At the same time, you know, I showed you the scatter plot of T versus F. If you draw a regression slope for all the different experiments, for the aerosol experiment, it is a little different. Not sure how much of that is, you know, just a signal to noise thing. But there may be a small systematic difference in the aerosol ERF.
Got it. Thank you.
Thank you.
And Torsten, do you want to close this out?
I guess I'm a bit slow today. I had a question for Helene. So you found, I think, 1.9, but you thought it should be 2.2. And then you saw drying in the reanalysis at the same time. So in terms of relative humidity, so maybe you explained it, but I just got confused, or maybe I didn't pay attention. Could you?
Yeah.
Speculate?
So we found 1.9 on a seasonal timescale. So there we don't have that relative humidity change. That's on an interannual timescale. And on the interannual timescale, we see a radiative response of 2.1 roughly. If we look at the second half, because the first half is heavily influenced by probably wrong relative humidity representations in the reanalysis. So if we focus on the second half, we get like 2.1. And we do see this drying trend. And this is what is really, yeah, it's kind of an open question for us as well, because we would expect if there's a drying, then it should be even higher. So this is why we think that it might be smaller than what we estimated before.
Right.
I don't know if that answers the
Two
question.
for constant relative humidity. So you would actually, with drying, you would expect even stronger negative, right?
Yes, because then you have less moisture and then more radiation can escape to space. So that should increase the response.
Okay, so it's still confusing.
Yeah, yeah, that's part of the point, I think.
Awesome. All right, let's thank our speakers again for a fantastic set of talks. And we will see you guys some point in the future. Just to say that there is a small chance we will skip July and August because we have lots of other conferences going on, but we'll let you guys know. Bye-bye.